Hey guys, welcome back. So in this video we're going to be going over the derivative. We're going to introduce the derivative, and then we're also going to compute the derivative using the long way, which is what I call whenever we take the limit of a difference quotient. And I know we thought that we left limits behind in the last chapter, but the good thing is that after we finish computing limits of the difference quotient, or the long way, we're no longer going to be using limits to find derivatives. We're going to be using their own derivative rules, which we'll be learning right after this lesson. So let's get started on the derivative. So here we have that a derivative is a blank. So in the most basic term, what is a derivative, right? So a derivative is just a slope. So that's exactly what a derivative is, and we're going to write that right in here. A derivative is a slope. All right? And now, let's say you want to talk about the notations of the derivative. How do I know they're asking me for the derivative if they don't actually say find the derivative, right? So, for example, let's say I give you f of x, and I tell you to find the derivative. I can also tell you to find f prime of x. So whenever you have f prime of x, I'm actually asking you to find the derivative. Another type of notation is when I give you y and I tell you to find the derivative, I'm just going to ask you for y prime. Y prime. And another way I can ask you for the derivative is when I ask you for dy dx, which dy dx means the change in y divided by the change in x. Alright? So all these three different notations all mean derivative, which is a slope or a rate of change. Alright? But let's talk a little bit more about what a derivative is, right? So let's say that to find the derivative or the slope, which is the same thing, we use the following. M tangent, and by M we refer to the slope, tangent, is equal to the limit as x approaches 0 of f of x plus h minus f of x over h. So this right here we refer to as the difference quotient. The difference quotient, which we've already gone over before. We've done some examples on what the difference quotient is and how to compute it. But now we're going to be combining difference quotient and limits put together to find this such called thing, a derivative, right? But a derivative just isn't a slope, right? Because you can't compute every derivative with our classic equation of the slope of y2 minus y1 over x2 minus x1. So that is not the only way to compute the derivative, right? So in this case, in calculus, we care about the derivative being referred to as the slope of the line tangent at a point, right? So if we have that word here, that keyword here, tangent, right? So what that keyword tangent means is, I'm going to show you guys here on a graph that, for example, I can pick this random point here at -1, and then I'm going to ask you to find the slope of the line tangent. So now I'm going to draw a line tangent to this point, and it's going to look something like this. So you guys see that the line tangent, and by tangent we mean that it makes a 90-degree angle at that point, the slope of that line is going to be negative, or m for slope is less than 0, right? So then we can also talk about a different type of slope. When here we have a slope of the line tangent, when it's completely horizontal, that is going to be a slope of exactly 0. And then let's say I tell you to find the slope here at x equal to 1, the slope of the line tangent right there is going to be positive. So whenever we're talking about derivatives, we're talking about the slope of the line tangent at a graph, right? So now let's go into computing the derivative and what exactly is going to mean the answer that we get, right? So this derivative that we get, what does it mean? Is it a number? Is it an equation? What exactly is this derivative thing, right? We say it's a slope. So we just think of slope as a number, and then we'll see if the derivative is always a number. That's a question that we can ask ourselves. So I've made you guys a little step box here on how to be able to compute the derivative using the long way, and since it's a very long, slow, deathly process, which we're going to make it through, I made you guys a step box so we don't get lost, right? So the first step we're going to take into finding the derivative is going to be computing f of x plus h, right? And that is the first thing I want to do, because I don't like to actually start doing everything in the formula, and you guys will see why in just a second. So let's compute f of x plus h, right? Which means that I'm going to input x plus h into every x of f of x. So here I have an x, and I have replaced it with x plus h, right? So that's what it means to compute f of x plus h. Now I'm going to go ahead and simplify this x plus h just a little bit. So I'm going to get 2x plus 2h plus 1. And if you're wondering how I got that, I just distributed this 2 into the x and into the h. Alright? So now I've done my step 1 of computing f of x plus h. Check. Done. Now let's go to step 2. In step 2, I'm going to be input into the formula. Okay, so I'm going to find my formula, which is up here, which is the m tangent, and I'm going to write this limit in red because we're going to be reminded of step 4, which says to apply the limit. Okay, that's the reason why we're leaving the limit in red. So then we're going to put the formula together. The good thing about this formula is that the bottom is always h, so we don't really worry about the bottom of this formula. We're mainly always dealing with the top and simplifying and combining things in the top. So let's go ahead and input things into the top. So the first part, which is f of x plus h, I'm going to put it in here. And then minus f of x, I'm going to put it in here. So for f of x plus h, I'm going to input this into here. And for f of x, I'm just going to input this into there. So let me go ahead and do that in blue. So I'm going to have 2x plus 2h plus 1. And then I'm going to input the f of x, which is 2x plus 1. Now I'm done with my step 2. I just input it into the formula. Done. Step 3 is the one that's always going to take a little longer, mainly because we have to simplify and combine like terms. And simplification may not always be the quickest thing to do. It may be a little painful, but we always have rules for every type of example. So let's go ahead. So here, by simplifying, I mean that I have this negative here that obviously I need to get rid of, right? And then I can combine like terms. So let me go ahead and draw another line. I'll go ahead and draw another line. Put h on the bottom, okay? And then combine like terms. So I'm going to have 2x plus 2h plus 1. Just drop that the parentheses. And then I'm going to distribute this minus, right? So I'm going to distribute the minus to the 2x, and that's going to give me minus 2x. And then I'm going to distribute this minus into the 1, the plus 1, and it's going to give me minus 1. So now that I've computed I've distributed the minus, I'm going to go ahead and, which is my step of simplifying, I'm going to go ahead and combine like terms. And by combine like terms, I go to the top of the fraction, and I'm like, okay, let's check this out. Here I have 2x and minus 2x. Those are going to combine, and they're actually going to cancel. And then here we have plus 1 and minus 1, so those two are going to cancel. So now let's go ahead and be a little more formal and write m tangent is equal to the limit as h approaches 0. And now we're going to go ahead and rewrite this. We're going to go ahead and rewrite this here. The m tangent is equal to the limit as h approaches 0 of, all that we have left is just this positive 2h and this h on the bottom. So we're going to go ahead and just leave that there, 2h and h. So there's also this hidden step that I like to always talk about when computing the derivative the long way, which ties on to step 3, which is going to be called our h check, right? So let me go ahead and write that maybe up here. So it's part of step 3, but it's going to be called the h check. And by h check, I mean that every term in the top, in the numerator, has an h. So look, we have a 2h in the top, the 2h has an h in it, so we're good to go. So now we have simplified and combined like terms. So right before we apply the limit, what we're going to do is we're going to cancel out h's, right? So right before we apply limit, we just cancel out h's, and that's part of combined like terms. And we're going to go ahead and cancel out this h with this h, so they're going to cancel. So now that I'm done simplifying, I'm going to set up my equation, what I have left, ready to apply the limit. So I have limit as h approaches 0 of just 2, right? of just 2. So now here, I am ready to apply the limit, and I'm going to input a 0 into every h. But guess what? I have no h's left. So when I compute the limit, I am just going to get 2. So I am done my last step, and I have applied the limit. Therefore, my derivative of f of x equal to 2x plus 1 is equal to 2, which means the slope of this line is equal to 2. So the question is, why is this just a number and not an equation? And the reason is that the slope of this line is always 2. So this is what we can call a constant slope, right? So that means that this line, which is 2x plus 1, right? If we look at it, we just graph it real quick. We just graph this line. 2x plus 1 is a constant function, so its slope is always equal to 2. And then if we also remember y equals mx plus b, the slope was just the m, and in this case the m here is 2, so that's another reason to tell us that the slope here, it is just 2. So in this case, we have to find the derivative of a line which has a constant slope. So our answer, our derivative, our m tangent, is equal to 2 because the slope is always 2 at any point. So the slope of the line tangent at any point of our function is equal to 2. But now let's go to example 2, in which we have a quadratic, right? And if we think about a quadratic, the slope isn't constant because depending on where you are in the parabola, so let's go ahead and draw it here real quick. Depending on where you are in the parabola, your slope is different. So if you're on the left side, right? If you're on the left side right here, the slope of the line tangent is going to be different than the slope of this line. And even if we're on this side, the slope of that line is different than the slope of the other line, right? So every slope here is different. So now we're going to discuss when we get the derivative, what does it mean to get, what does the derivative exactly mean here, right? So let's just kind of have that graph there. Let's erase all these yellow lines, all these red lines. Okay? And now we're going to go ahead and find the derivative. And to do that, we're going to erase all this stuff because now we have a new checkbox to start checking out. So now we're going to start off with step 1, which says that we're going to find f of x plus h. So we're going to input into every x in f an x plus h. So we're going to have x plus h squared minus 1. So this f of x plus h is actually going to take a little longer than our previous one because we have a parabola, so we have a quadratic, and it takes a little more work. So let's go ahead and do that. So now we're going to go to f of x plus h times x plus h. So real quick here, big common mistake when computing f of x, when computing x plus h squared, is that we love to be lazy and we love to say that x plus h squared is equal to x squared plus h squared. We just kind of just dump this 2 and square this and then square that. But that is not true. That is not true. Alright? You have to actually multiply x plus h times x plus h. Very common mistake. Please don't fall for it. So let's go ahead and keep computing the f of x plus h. So it means we're going to distribute now. I know it's longer and more annoying to follow this, where we distribute x times x, which gives us x squared, x times h, which gives us xh. Then we multiply now these bottom two. So h times x and h times h. So we're going to get x times h plus h squared minus 1. Now we're going to combine our terms here, because if you guys notice, we have x plus h and x plus h. So that is going to give us x squared plus 2xh plus h squared minus 1. So we have computed the f of x plus h. I'm just not going to write all those. You guys got it. It's a bunch of f of x plus h. And now we're going to go to step 2. We're going to go to step 2, in which we input into the formula. So we're done with step 1. And now we're going into step 2, which inputting into the formula never really takes that much time, but the simplification part is the one that actually always takes a lot of time. So let's go ahead and do that. M tangent is equal to the slope, which we're going to do the limit. We're going to have it in red, so we can always remind it to take the limit last. We're going to leave the h in the bottom because it just kind of chills there in the bottom. And then we're going to have f of x plus h in here minus f of x here. So let's go ahead and input that. So f of x plus h is x squared plus 2xh plus h squared minus 1, which we just got from right here, which we already computed. And now we need to input our f of x, which actually comes straight from the formula, which is going to be x squared minus 1. So now we've done step 2, which is usually our easier step. We're going to go ahead and simplify and combine like terms, along with our last step, which is the h check. Let's remember that. So let's go ahead and draw our line. So we have h in the bottom just hanging out. And now we're going to simplify by just dropping this x squared plus 2xh plus h squared minus 1 just down here. And now we're going to make sure to distribute this negative into this one and into this one. So we're going to have a negative x squared plus 1. Remember that this negative here times this negative here is going to become plus 1. And now that we've distributed our negative, which we can consider for our simplify, we're going to go ahead and combine like terms, which means that we're going to go look alike. We're going to go look for the terms that are like x squared. It's going to go with this x squared here, so they're going to cancel. This positive 2xh is just going to come down by itself. This h squared is going to just come down by itself because nobody else matches them. And this negative 1 is going to cancel out with this positive 1. So what we have left is this 2xh plus h squared with this h on the bottom. So we're going to go ahead and draw another line in which we're going to have, go make myself a little space there. So there we have 2xh plus h squared. And now we're ready to do our h check, which means that we're going to check that every term in the top has an h. So let's go ahead and do that. And we check that the first term has an h and the second term has an h. So now we're going to go ahead and factor out this h. So let's be a little less sloppy, making sure that we have all these limits here. And now we're going to have another limit here. We're going to go sideways now for a second. So now we're going to factor out an h, because they both have an h. But why factor, right? You may be asking yourself that. Why factor? Well, because we have this h on the bottom. And this h on the bottom, the goal is always to get rid of it. So we want to just get rid of that h. So how we do that is we factor out an h from the top. That's why we do the h check, to make sure that we can factor out an h, so we can cancel with the one from down there. So that we can cancel it from this h right here. And now that we cancel our h, we're done with step 3. And now we're going to apply our limit, which is our final goal, right? So now we're here. We have that the limit as h approaches 0 of 2x plus h is equal to, and what do? We just simply input the 0 into this h. So it's going to give us 2x plus 0, or that's also equal to 2x. So the slope of the line tangent, or the derivative, is equal to 2x. And you guys see how we actually have an x in this derivative? And the reason for that being is that depending on its location, how we discussed earlier, depending on its location, it's going to affect what our derivative is. Right? So here I'm going to ask you to find the slope of the line tangent at x equal to negative 2. So let's say we go to our graph, right? So let's go straight up to our graph. And negative 2, let's say it's like here. And let's say that's where it hits the graph, right? It's on the negative x-axis. And I'll just draw the line tangent. Maybe it's like that. We don't have to be too specific. That is the line tangent at x equal to negative 2. But let's say I want to be exact and I want to find the slope of that line. I'm just going to input x, my x value, my negative 2, into my derivative. So let's use a little bit of notation that we learned earlier here. So since I'm given f of x, my derivative is going to be f prime of x. And that is going to be equal to 2x. And now here I'm asking you to find the derivative at x equal to negative 2. So I'm actually asking you to find f prime of negative 2. And by x prime of negative 2, I mean that you're going to input negative 2 as my x value. And then I'm going to get negative 4. So as I get that my derivative at x equal to negative 2 is negative 4, that means that my slope is negative. The slope of the line tangent is negative, and it obviously shows that we have a negative slope here at negative 2, right? So when we find the long way derivative, that gives us an equation for any slope, for the slope of any at any x value, right? It gives us a general equation for our slopes at any line tangent. So here, since we have to find a specific value, the specific value in this case is negative 2, it gives us the specific slope. While when we find the derivative the long way, it gives us an equation for any point. Okay? So now let's go check out example 3, which is just the same idea. We still find the derivative the long way, but here we're given a fraction. So in this case, the fraction has actually different tricks that we need to do in order to compute the derivative. So let's go ahead and start off with step 1, which is f of x plus h, which in this case I'm just going to input x plus h in the bottom, which that's where the x is. So that was an relatively easy x plus h. Now I'm going to go to step 2, which I'm going to input into the formula. So m tangent is going to be equal to, let's make sure we have the limit here in red, so we can always remember to take the limit. That's when we know we're done. And we're going to go ahead and write f of x plus h is going to go here, minus f of x over h, right? H always goes in the bottom. That's guaranteed, never changes. And now we're going to have 1 over x plus h as our f of x plus h, and which we got from here, just got straight from here. And then for our f of x, we're going to input 1 over x, which we got from here. Okay? So let's go ahead and do step 3 now, which is simplify, right? Step 3, which is simplify. And in this case, we have fractions. And like I told you, we only really care about simplifying the top because the bottom's just h. So how are we going to simplify this, right? And in order, we have two fractions subtracting. I know, fractions, they're not easy things to deal with. But if you guys remember when we had to subtract fractions, we always needed to find a common denominator. Exactly. So a common denominator is what we need here. And we're going to go ahead and find that. And if we have x plus h, and then if I have x, then my common denominator, my easiest bet is just going to be multiplying those two together. So I'm going to multiply this guy by x, and I'm going to multiply this guy by x plus h. Alright? So therefore I have my common denominator. But if I multiply those bottoms by x and the other bottom by x plus h, I also need to multiply the tops by x. I also need to multiply the top here by x plus h. Just because I need to be fair, and then whatever I do to the bottom, I do to the top. So I don't actually make any changes. I'm just modifying so I can actually subtract these two fractions. So let's go ahead and write that line. I need a little more space. So that line right there. So we're going to go ahead and keep having our f of x plus h, right? But now we need to actually simplify each fraction, right? So here I have 1 times x on the numerator, so I'm going to have just x on the top. And this is going to be x plus h. And the reason why I do that is just so I make sure that I have my denominator in a nice organized form, having x first. And then here I have 1 times x plus h, which is just going to be x plus h. Then I'm going to have x on the bottom times x plus h. So now I have the same denominator, so now I'm ready, and I've fixed my tops, I've simplified my tops, so now I'm ready to just combine. And by combining this one, I just mean subtract these two fractions. Now, since these two fractions have the same denominator, I can just write one denominator, which is going to be x and x plus h, and then I can just worry about subtracting the tops. So from the top here, I just have the x to worry about, so that it's just going to be x. Done. But now when I'm going to combine the right side of the top, I'm going to have to take into consideration this negative distributing into the whole x plus h, right? So we actually have a negative distributing times the whole x plus h. So that means that I'm going to have a negative times the x and a negative times the h. So that is going to give me minus x. That is going to give me minus x minus h. Alright? Now let's take this time here to catch up and put some limits. So now that I have subtracted my fractions and I have fixed my top, I'm going to go ahead and combine like terms. So I'm going to go ahead and get this x here and this minus x here, and they're going to cancel each other out. So now let's check here what we have. All I have left is just that negative h divided by x plus h. And that's going to be over h, right? So I do my h check, and everything on the numerator has an h. But what exactly is my numerator? Is it going to be this h, or is it going to be the whole numerator? But guess what? In this case, we're not even going to deal with this function like this. What we're going to do is we're going to be dividing these two fractions, right? Because we have a fraction on the top, and then we have a fraction on the bottom. And you may think, no, I don't have a fraction on the bottom. I just have an h. But how do I make this h a fraction? I'm just going to divide it by 1, right? So now if you guys remember from dividing fractions, what you do is you keep the top fraction the same. So it's going to be negative h over x times x plus h. And then we're going to multiply it. We're going to multiply it by the reciprocal of the bottom fraction. By reciprocal, I just mean I'm going to flip it. So h over 1 gives me 1 over h. And the ideal goal of that h check anyway was to cancel out the h's. And guess what? I'm going to do just that here. I'm going to have an h here, and it's going to cross out with this h right here. And I'm done. I'm done with the simplifying part, right? So after I'm done simplifying, what am I going to do? I'm going to be left with a negative 1, because I have a negative from here, and I have a 1 here, so it gives me a negative 1. And I'm going to have an x and an x plus h on the bottom. So my next step here is just going to be to apply my limit, because I'm done. I have the red apply limit done. So I'm going to go ahead and apply my limit. So I'm going to input the 0 wherever I find an h. It's going to be right in there. So to apply my limit, I'm just going to have negative 1 over x times x plus 0, right? And then if you guys notice, that is just like saying x times x, because x plus 0 is just x. So what's x times x? I'm going to remove myself. It's going to be x squared. So my final answer is negative 1 over x squared, and that is the slope of the line tangent, or my derivative. So there we go. Now we're done with this very lengthy problem, which I thought it was never going to be over, but it is. So now we're done computing the derivative the long way. So now let's go check out some practice problems on how to do the derivative the long way, in which we're going to cover how to do radicals and other types of scenarios, because every time you have to simplify, it actually changes depending on the function. So I want to make sure you guys are exposed to every type of problem, so there'll be no surprises. So let's go ahead and do some practice problems, and after that, we're ready to say goodbye to limits to find derivatives, and we say hello to derivative rules. So see you guys next time.